Hello everyone, we're Group 8 and we want to analyze the NBA player salaries in this project. The player salary is an important factor to investigate, while the team managers need to use high wages to attract talented players. It is also important for them to appropriately evaluate the player's value in order to balance the cost for the team. For these reasons, among all the different variables, salary is one that remains the most crucial and will be the main focus in our group. With advanced machine learning algorithms, player salaries can be analyzed accurately based on their performances, and in this way, salaries can be distributed to players accordingly. In this project, our team used an NBA database with data on thousands of players' salaries and performances. We utilized both inference models and prediction models to investigate how different factors influence the player salaries and use their corresponding significance values to predict their wages. For the inference model, we applied backward and forward selection based on a control number of variables in order to eliminate some variables of lower statistical significance and get a clearer interpretation. Then we used the k-fold cross-validation method to add polynomial terms that most efficiently explain the variation in player salaries. The result is a model that is easy to interpret, referencing only some key player statistics, yet very effective at explaining the variations in salaries. In the prediction part, the dataset is split into train and test datasets. We apply 5 different models, OLS, backward, forward, ridge, and lasso to select the most associated features in predicting the player's wages. Then we evaluated the performance of different models generated from the training dataset to the test dataset and assessed their accuracy by comparing the mean square errors. The dataset is basketball-related and consists of more than 7,000 NBA players' observations. The dataset contains 39 variables, including both numerical variables, such as the average salary of both players in each team for each year, and factor variables, such as the player's ID code and the team they play for. From the numerical summary table, we can see that the variable salary has a mean value of approximately 4.6 million and a median value of approximately 2.6 million, which implies a potential rise skills pattern. In addition, it has a mean value of about 4,000 and a maximum value of about 37 million.
Now let us come to preliminary analysis. First, let us come to our outcome variable, which is yearly salaries. The salaries variable records players' contracted earnings in a single season. Note that contracts are usually signed on a multiple-year basis, and salaries are sticky in some cases and do not often respond to changes in explanatory variables right away. So, according to the data, the players' yearly salaries are skewed heavily towards the right. The logical interpretation is that the league is composed of a majority of players earning a medium-sized contract and a very small portion of players earning contracts which are many standard deviations larger than main contract size. And here is the distribution of yearly salaries across all players for each season from 2001 to 2019. And from this figure, we can easily find out that the yearly salaries of players are skewed towards the right instead of being normally distributed. And then we got our explanatory variable, which is the points per game. This variable is usually the first thing people look at when they try to determine the basketball player's ability. The NBA also acknowledged the importance of points per game by giving out the scoring champion award each season. Since the fundamental way to win a basketball game is to score more points than opponents, having a player who scored more points is trivially considered to be a factor that leads to more games won per season. considering the that win more games are likely to generate more ticket revenue. Players who score more points per game are also likely to earn more salaries than those score less. However, an increase in points per game does not increase the salary immediately, as players are usually signed to contracts that last for more than a year. So a better way to run our model is perhaps to use the variable points per game in the season before, since better performing players getting better contracts in the next season seems to be an intuitive interpretation. And here is the scatter plots between points per game in 2009 to 2010 season and salary in 2010 to 2011 season. You can also find the positive effect between these two variables. And then we got another explanatory variable, which is the age. This variable also plays a very important role in determining the future of a basketball player. The age group 28 to 32 are the most heavily played, and the further away from that age group, the less players are paid. According to past experience, the athletic performance of humans usually peaks before the age of 30, and from there on, they will fall into decline. As the age grows older, the mass, strength, and function of muscle gradually decreases. And furthermore, the endurance also drops a lot as the body uses oxygen less effectively over time. Therefore, we can expect that for athletes older than 30 years old, younger players tend to have a brighter future than an older one, because the younger player, his body capacity still has space for development, but the older one needs more time to adjust their bodies. However, for athletes younger than 30 years old, as their body capacities are still moving upward, the team will be more attracted by the experience and technique of older players. Thus, the older players tend to have a higher wage than the younger one before age 30, before the age 28 to 30. And here is the box plot of yearly salaries by age group of different athletes. And we can easily find out that the age group from 28 to 32 earns the highest wage.
Okay, so moving on, we got our inference model. And to begin with the inference model, we aim to do better inference framework. We aim to have better interpretations of our coefficients compared to prediction models. So inference model is going to be slightly simpler and slightly more interpretable. So in terms of methodology in inference model, we did some stepwise selection and we used some residual plotting, and we figured out that residuals seem to have a relationship with the axis, and we set up some solutions for those. And okay, so to begin with, we used forward and backward selection to eliminate some of the variables to give us more simplicity at the cost of relatively low decrease in predictive power and explanation power. And basically, stepwise selection compared to best subset selection requires far less computing power, and it eliminates some of the unnecessary variables. And we didn't allow interaction terms here, also because adding those just gives much more complexity to the model than needed for an inference model. And so for stepwise selection, we used BIC, the Bayesian information criterion, as our judgment, basically metric for the best model, because it implies slightly more, as you can see here, slightly more penalty for large numbers of variables, and we definitely don't want a large number of variables in our inference model, because these variables, especially performance metrics, could be implying similar things, such as offensive and defensive rebounds by the player, and they pretty much measure the same rebounding ability. So we definitely want to limit some of our variables. And after that, we did some residual plotting. That is after we selected the best kind of subset, even with backward selection. and I think we did n equals 17. So we had 17 variables in total. And after that, we plotted basically residual plots for each of those variables. This is not everything, but this gives a pretty good overview of how other variables than age have basically no problem with their residuals, but age has clearly a non-linear relationship between age and residuals. So we wanted to fix that, and basically there are several solutions to this. The first solution is to kind of to look at this pattern of the residuals, and it seems that there is this inverse quadratic pattern that there is like a peak in the middle. So we are under predicting people at the peak, and we're over predicting the salaries at each ends. So one approach would be to add a polynomial term to explain this. And the pro of this is that it can be interpreted mathematically, as in we can simply just take the derivative of h for the coefficients, and we can basically mathematically explain like what happens when one player gains additional basically year of age. And the con is that if we ended up needing more than 2 degrees of polynomial, it can be very hard to interpret, because once the degree gets higher than 2, it's hard to say like where exactly turning points are and what exactly is going on in the population. And the other approach to adjust for this is to, take basically every 4 years of age and group them into one age group, and basically treating age group as a factor variable and say that they all have different levels of expected salary. And the pro of this is that it's very easy to interpret. It's very easy to explain to people how exactly this works. We basically just say like which age group has basically the highest salary. But the con of this is that we cannot really say much about the underlying relationship, as if we cannot do the derivative approach, and we cannot say that what exactly like if you gain 1 year of age in this age group, there's obviously also a difference, but from our perspective, this is not going to be different because they're all in the same age group. So here are results from the cross-validation. So we used k-fold cross-validation with k equals to 10. This is to say that we split the data into 10 parts, and each time for 10 times, each time we leave one part out as the test data set, and then we basically see how the model will be trained them in the other 9, and what is the mean square error for the test set. And the one on the left is when we use age groups, and as you can see, it's way lower. The mean square error is way lower than when we didn't have any polynomials or the age groups. So this is the one on the right, and then as we go to the right is when the polynomial increases. This is n equals to 2, this is 3, this is 4, and this is 5. And theoretically, the best choice here in terms of limiting, best predicting people's salaries is probably n equals 4 polynomial, but that is very, very hard to interpret what's going on. And I'm not sure if this is what we want in the inference model. And it seems to us that by using the factor variables of age group, we are actually do a better job than using polynomial terms when n equals to 2. So in the end, we decided to go with this factor variable of age approach. I think it's just slightly favored over polynomial terms because of its relatively easy interpretability, and then it also kind of explains a lot of variations here, at least compared to n equals to 2. And so in the end, for our interpretations, we thought that basically all the variables, the coefficients made a lot of sense, especially the ones with the performance metrics such as points, assists, rebounds. Those are all highly positively correlated with age, and they're quite significant as well. But there's also things like minutes per game, which suggests because it's negative correlated with salary. So this basically is just suggesting that if you have the same points, rebounds, assists, basically the same contributions as the other player, then probably if you take more minutes on the court, it means like you're taking up minutes for your teammates. So you're probably not as efficient, and your salary is not as high. And Also, there's a clear upward trend of salary over the years, basically from 2000 to 2020. So if a player performs the same in 2000 and 2020, then he is predicted to earn more in 2020, much more than 2001. So, and also like basically field goal attempts, the higher the attempts, the lower the salary, because this is also kind of adjusting for the percentages and basically shots made. So if you have the same shot made and you take more shots, it probably means you're also less efficient. And in the end, for the age that we cared the most about, it peaks around 28 to 32 years. So this is the age group that has the most salary. And if you go either way, then salary is going to decrease. This just means that this is the performance peak of the players, likely because that as you age, as you go into the league, you gain more experience as you age. And then after this 28 to 30 years old, you're probably likely to, your body is going to deteriorate as you grow older.
So now after running the inference model, let's now turn to the prediction model. In investigating the predictive power of different variables, our group utilized 5 prediction models, which are OSL model, backward selection model, forward selection model, ridge and Lawson models. First, before running the models, we need to apply the train test split. Our group split the whole dataset into 2 sets based on the players instead of the normal splitting method. The original dataset contains the salary of the same player in different seasons. Considering the salary of the same player, even like in different years, can be really similar. So our group extracted the name of the players from the dataset and then split the names into train test datasets. Therefore, similar salary and performance data of a particular player will be guaranteed to be placed in one dataset, either in the train or the test dataset. And thus it can better avoid the overfitting problem in different models later. So for the models part, first we generated the OSL model with 24 linear variables and their interaction terms. Then to provide a more accurate result, our group applied stepwise selection method, specifically the forward selection and the backward selection. The stepwise selection model, a selection method is a method of fitting regression models in which the choice of predictor is carried out by an automatic procedure. In each step, one variable is considered for addition or subtraction from the set of explanatory variables based on the standard of MSE from cross-validation, ACE, PCE, or adjusted R-squared. In plotting the outcomes of both forward and backward selections, our group uses adjusted R-squared as a standard to judge the level of fitness. Adjusted R-squared imposes a slight penalty for increase the number of variables to prevent overfitting. So it will only increase when the additional variable has significant explanatory power and provide more accurate information regarding the performance of each variable in the model. Thus, it can be a better criteria when comparing different models later. Besides backward and forward selection, our group also applied ridge and Lawson models to select most associated features for future prediction. Both ridge and Lawson models managed to prevent overfitting through shrinking the coefficient estimate toward 0. While applying this to models, the algorithm is not only trying to minimize the RSS of the model, but also trying to minimize the combination of RSS and the shrinkage penalty term, consisting of the coefficient and the parameter lambda. Thus, coefficient of features that are not associated in predicting the salary will actually shrink to zeros. We apply the ridge and Lawson algorithms on the model with both linear terms and also the interaction terms. In the ridge regression, the algorithm selects different lambda values ranging from about 12 to 22. For each log lambda value, the algorithm applied the cross-validation method to split the dataset into the train test dataset and then measure the MSE of different groups. Our group choose the model with the minimum MSE as the best model and save the capped variables in that model for future evaluation. Also, for the Lawson regression, the algorithm applies similar technique as a ridge regression. The algorithm also selects different log lambda values and then run the cross-validation method for each log lambda values. According to the resulting figure, we selected a model also with a minimum MSE as the best one, and then kept the variables in that model for future evaluation. So here, like this picture shows the MSE of the cross-validation according to different log lambda value in the ridge regression. And this shows the MSE of the cross-validation according to the log lambda value in the loss regression. So here's the result. So after running all the 5 models, our group generated a table with all the chosen variables and their corresponding coefficients. This table contains like nearly 300 variables, so we do not attach the table here, but the result table is in our paper. So by applying the 5 best models generated from 5 different algorithms to the test data set, we get the MSE for the 5 models as shown in this slide. In the bottom. So in comparing the MSE, we found that ridge and Lawson models tend to have better predictive performance than the other 3 models. Even though the backward and the forward models have smaller MSE compared to the OSL model, the stepwise model's performance in our case did not really improve much compared to the OSL model.
Salary reflects the evaluation of the player's performance within a time period and the expectation for their future performance. It motivates the individual players to work harder so as to benefit the team in the long run. Our models explain critical variables that affect players' salaries. In the preliminary analysis, variables including season, points per game, ages, and minutes played per game have a strong influence on the player's salary. The increase of points per game and minutes played per game are associated with an increase in the salaries. Age variable shows a nonlinear relationship in the chart with the highest salary from age 28 to age 32 and lower salary outside of this range, which indicates a higher polynomial association in age variable. For the inference model, we use BIC to reduce the number of variables and to have a clear interpretation. And then we use the residual plotting to add polynomial terms to the regression. We use OLS backward selection, forward selection, ridge, and Lawson models for prediction. Among all the models we use, the ridge model has the best prediction accuracy. Overall, shrinkage models have better performance in fitting the data sets and predicting future salaries compared to stepwise selection methods. Our prediction and inference model attempt to decipher the driving forces behind a player's salary. The similar application can be extended to many other sports, such as NFL and MLB. Machine learning has shaped how the salary will be estimated in the near future. Thank you for watching. That's our inference and prediction on NBA salary.